Today I'm going to be going over this stiffness limited design project that you guys have been assigned. I'm going to be going over how to get started, what the deliverables are, and a few tips and tricks that I have from doing the same exact project last year. Here are the deliverables. You want to do a simulation on Autodesk Inventor. We'll cover that. We want to estimate the force on the springboard by the weight of our diver, Jack Laffer, and we'll see that in the YouTube video. And then you guys are going to list 10 different materials that could replace the current material used for these diving boards that's standard for all of our Olympic and world competitions. So find 10 different materials, and then you're going to select which material is best for the least amount of weight, the lowest cost, the lowest environmental impact, and the best overall. Now, we can't just go willy-nilly and choose any material or the lightest material for the least weight, the lowest cost for the cheapest material. That would be too easy. We need to find a constant flexural rigidity, and we'll get into what that is to make sure that the standards of the competition are upheld. So what is flexural rigidity? So this is the equation that we're going to be using for this entire project. So this is called a cantilever beam. It's any sort of beam that's mounted on one side and is deflecting, right? So in our case, we're going to be using a single load at the very end of the beam that represents our diver right here, right? So our equation is PL cubed over 3EI is equal to our maximum deflection. So what does this mean? P is our load, so that's going to be our weight of the diver. L is our length of the beam. And EI is what we call flexural rigidity, right? So it's made of two components. Flexural rigidity is equal to E times I, E being Young's modulus, which is a material property that you guys have probably talked about a little bit, and I is area moment of inertia. So as you pick different materials for, like we said, the least weight, the cheapest, etc., it's going to change your Young's modulus. So you need to be able to create a design with a different area moment of inertia to where the product of E times I is equivalent throughout, right? So this means it's going to deflect the same amount, not messing up the competition due to a material of a different use or a different material being used that's going to affect the deflection, right? So I talked about area moment of inertia being that I value. Let's talk about what that is exactly. So if we scroll down in this PowerPoint, and there's a ton of good equations in here that you can use to find, different values such as cost, weight, effectiveness. But let's look at this table here, right? So this is our area moment of inertia table. It's also called second moment of area. It's always a length or distance unit to the power of 4. So a diving board very closely resembles a rectangle, but there's a few differences. The equation for the rectangle is BH cubed over 12. Right, it'd be really easy if we could just use this one, but unfortunately it's not exactly a rectangle. As you can see in this picture here, right, there's these little ridges on the bottom. So it's not exactly a rectangle, so we can't use that equation. But know these equations, they're good to know, especially in your materials and mechanics courses. But I'm going to show you a way that you can find area moment of inertia within Inventor with only a few clicks. So here we have kind of just a brief little sketch that I made of what the cross-sectional area of this diving board looks like, right? So you have the board, you have these little ridges that I was talking about, and what these ridges do is they actually add more vertical area to the overall area, right? And if we go back to this equation, look at that H, it's cubed. So that means the more vertical or H value that you have, the stiffer it's going to be, right? It's going to take more force to bend it. So that's why these little ridges are here. It allows them to have the same or more stiffness with less material, right, and less cost. But here's how we can find this in Inventor. So we want to right click on our sketch, go to edit sketch, or you can do this while you're making your sketch as long as you're in the sketch view. Then you're going to right click again and go region properties. So this is an awesome tool you can use. You select all the area that would be, part of your physical design, calculate, and then you're going to get these two values right here, area moment of inertia with respect to principal axes, right? Like I said, it's a distance unit to the power of 4. You have one for your inertia about the x-axis and one for your inertia about the y-axis, right? So let's take a look at our axes. imagine the diving board is extruded this way. And you know what? I'll actually extrude it right now so you guys can see what I'm talking about. There we go. So now it's extruded, right? And we can kind of refer to this, the little origin in the bottom left corner. It's going to be bending around this x-axis. So we want to take that inertia about the x-axis value, okay? So that's kind of all the theory and mathematics around it, right? I really want you guys to understand that as you select a different material, it's going to have an impact on the deflection, but we can control how much it deflects by our design of that cross-sectional area, right? As we change those values, it's going to change our I value, which will in turn change our flexural rigidity as we balance out to get the same deflection value. So let's go ahead and get into the actual stress analysis that I talked about earlier, and I'll show you guys how to do that. So you click stress analysis, right? And then create study. Everything looks good. Okay. So the first thing you want to do, and arguably the most important, is you want to assign your material. So you go over to this left side right here, right click on material and assign material. Okay. And then we can see a list of all of the, base materials that come downloaded with Inventor, right? If you want to do a more exotic material that maybe you find in your textbook or in your research phase, you may have to download those material properties or even create a custom one, right? But for now, let's just use aluminum 6061, right? So we're going to load that into the design, add materials to document with this little arrow right here, right? Aluminum 6061. Now we can see that our part one is made of aluminum 6061. So it's going to have all the material properties for the material. The next thing we do is we're going to add our constraints, right? So if we're imagining that our diver's over here, right, he's jumping up and down, we want this to be constrained on this side, right? And it doesn't really matter what side you do this on, as long as you kind of understand what's going on, right? And so it's really important that you constrain this the proper way, because we don't want any of this face to be moving, right? So when we add our constraint, we want to do a fixed constraint, right? And we want to constrain this entire area. So that means no point on this cross-sectional area is going to be moving due to that force that we're about to apply, right? So we apply that constraint, going to exit out of that. And now we want to go down here and we want to add our force. So this is going to represent the weight of our diver at the end of our board, okay? So we want to select this line right here, and it might be easier if you zoom in, but we want to select that line, and what it's going to do is it's going to automatically going to apply that force to the midpoint, right? So it's right in the middle where our diver would be, but we can see the arrows pointing the wrong way. It needs to be going down. So we click on these two little arrows right here, and we press use vector components. So now you control the vector, which is going to be magnitude and direction, and we're only going to put a force in our y direction, going down with gravity. So we want to do minus, let's say Jack Laffer is 150 pounds. I'm not sure if he is. You can probably find that out by Googling it or going to his Wikipedia. Minus 150 pound force. Make sure you get these units right. So now we can see it's pointing down. Okay, so everything's good. We have our material, our constraints, our loads. Let's go ahead and do the analysis. And then we're going to press, oh, sorry, I exited out of it. Didn't mean to do that. Should still, all right, it's still set up. Simulate, not finish. Here we go. We're going to press run. Might take a second. So while we're waiting, let's talk about a few of the tips and tricks that you guys can do, right? So you're going to be redesigning this cross-sectional area for each different material that you use. So one thing that I found that was really useful for this project, instead of redoing that calculation over and over, you can put it into Excel one time and create a bunch of different columns for the different materials and then different physical properties of this cross-sectional area. So maybe it's a different number of ridges or depth of ridges or area, etc. that's going to give you that same exact flexural rigidity. And then you can scroll through those, find the flexural rigidity that is most similar to what you need, and slightly tweak the design until you get exactly that E times I value that you want, right? And so I'd recommend doing that for all 10 materials, and then maybe in your paper actually showing the calculations for the 4 that you choose, and especially the best overall. Okay, so now we can see our stress analysis is done, right? This looks about right. Looks about how much it was deflecting in the video. So we know we're on the right track, but we want to know exactly how much it's deflecting. Okay, so right now we're looking at our von Mises stress, right? We want to go to displacement and then Y displacement. Okay, so now we're in our Y displacement. It's going to show us how much it's displacing in this axis right here. So obviously we have 0 down here where it's constrained. Then our maximum is at this very tip, 6.363 inches. So we know if this looks similar and that value right there is similar to the deflection value we find when we count the pixels of the YouTube video, we know that we did it right. Okay, so that's pretty much all there is to it, right? You want to have all that stuff, do it for your 10 materials, select the best overall, and highlight what you find. But I appreciate you guys paying attention and tuning in. Good luck on the project.